Hello, friends. Welcome to Science Talk. I am your host, Jim Massa. And in this video presentation, I want to discuss with you what we see right here, gases, temperatures, and ice. Basically, I want to bring to you the latest data on those three major topics and have a discussion of what the data is informing us of. So before we get going, I think I'm going to make myself disappear here. Okay, so first thing we want to look at are the gas trends of carbon dioxide, methane, and nitrous oxide, CO2, CH4, and 2O. Let's start with CO2. So what do we see here? We have the global mean CO2 abundance. We have a chart here on the vertical axis in parts per million, starting from 300 up to 900, maybe 950 at the very top horizontal line. We see going from 1750 projected out to 2100. 1750 is now considered to be the start of the industrial age, at least in its infancy. Probably didn't really get going until a century later at 1850 when it really kicked into place. So the data is coming from a number of places. It's coming from the IPCC, and this 2013 report from that table, looking at ice cores. So you measure the gas concentration in the ice cores. It comes from NOAA, and we're seeing here different scenarios that the IPCC is projecting. So this is one type of model, another type of model, another. So basically, the four different models that they looked at. Now, you can say, so why are there so many? These are projections, because here's 2020, approximately right about there, pretty much right at the junction where I have the cursor there, okay, between a red and a black. So why the different projections? It depends on the models, depends on the assumptions that the models are making. That goes to cloud cover, that goes to whatever interactions they are accounting for, or whatever trends they are looking at, depends on the equations that they're using. But basically the models, so right up to about here, is what the measured data is telling us. Now, you look at this here, if you drag this across, we're about there, so it's about 410. We do know that based on readings from Mauna Loa, as well as in a station that Australia runs in Tasmania, the level is about 414 or so. That's the current level as of July into August. So different models. This one shows a flattening, so that increases maybe about 420, 425 or so. Then we have another model bringing us up to about 500, then close to 700, and this one is well over 900. I did a recent video segment where I discussed, in the video segment was lessons from the early Eocene, where some of the modelers were suggesting temperature increases of up to 9C is a possibility by 2100. Well, if you get this much CO2 in the atmosphere, that is a very likely outcome. But the take-home message is that for the most part, through at least 2050, except for this one here shows us flattening, the increases are expected to, levels of CO2 are expected to increase. So here's the atmospheric abundance at Mauna Loa. So if you look at the red line here, you see it goes up and down in an oscillatory manner, and it starts from basically 1960 through 2020, so a 60-year record, parts per million on the vertical scale. The oscillatory nature is reflecting seasonal variation. There will be seasonal cycles in the levels of CO2 and other gases for that matter. The important thing is the black line that runs through here. That is a 12-month running mean. So that means you calculate the average for, January, and then for February, March, etc., all the months, and then you calculate a mean for those 12 months. So you go from January to December, then February to January, March through February, April through March, etc., etc. That's why when you look here, the black line stops, but the red line continues, because they still have to compute the average from prior month. Putting that aside, we see the trend is very clear. CO2 is increasing rapidly. So now if we look at, this is a delta CO2. So this is measuring the actual level of CO2. This is now calculating the change in CO2. Parts per million per year. Now it's telling you how much CO2 is increasing every year. Once again, we see the monthly mean in red, then the 12-month running mean. So the monthly mean, right, going back to here, monthly mean, right, showing the month to month, which reflects the seasonal variability. Then from the month to month, you calculate the 12-month running mean. They do the same thing here. And as you can see, the 12-month running mean follows closely the monthly mean, which is to be expected. But here's the thing. The blue line is the linear change. As you can see, we have positive slope. So you can easily calculate the slope of this, as to basically, if I took from, say, 19, with the cursor, if I took, say, 1970, where it's changing at, from the prior year, it added one more part per million than previous year. And then I looked at where across 2, that's about 2000, well, let's see, where is it? About there. It looks about 2005. So for 35 years, you can actually, 1 over 35, and that will give you about a 0.03 approximately parts per million increase, linear average per year. Excuse me. So that's what this, look, this is a straight line, so we can get a straight line slope from it. I'm just doing a quick estimation in my head, but it's about 0.03 parts per million per year over the long haul. It's still increasing. That's still no. So if it's a 0.3 per year, if you were to extrapolate this outward, assuming linear, then in 100 years you add 3 parts per million. But we know what? We know that it's increasing exponentially, so that would actually turn out to be an underestimation. Now this is looking the same information, but instead of being at Mauna Loa, it's now looking at the globe. So the previous graphs are looking at information taken at Mauna Loa. Now we're looking at all of the stations all over the planet, collecting information. As you can see, monthly means in red, reflecting the oscillatory nature of the season. And then you fit the 12-month running mean through that, and you can see the clear indication. And now you can see that is well above 410. Once again, the black line stops before, because we have to, it kind of lags behind. So you have to kind of go wait for the next few months to come in, wait for the next year, the next 12 months period to pass by, and then you can update that. But the trend is clear. Same thing as we see here, except now they're doing a 60-month mean, so that's a 5-year mean. So they didn't calculate necessarily well, this is not a straight line, so you would have to take the derivatives to find instantaneous rate of changes. Putting that aside, though, we still see, especially starting from about 95 or so, we see overall an increase in global atmospheric CO2. Now let's look at methane. First of all, note the scale. The scale is in parts per billion. Okay. So if you want to know what the equivalent would be parts per million, take these values, divide by 1,000. So this would be like 3.5 parts per million, 3 parts per million, 2.5, etc. They chose to represent as parts per billion. That's fine. So 1,000, 1,500, etc. So we have the same data sets, the same modeling. This here is showing, a decrease in the methane. And for most of these extrapolations, they show a decrease by the year 2100, except for this one here. So a little difficult to know what methane is going to do, because part of the problem or the issue with methane is that it doesn't linger in the atmosphere as long as CO2 does. Even though it is a more potent greenhouse gas, trapping more heat energy per molecule, it doesn't persist as long in the system as the CO2. So that could be an explanation for some of these different modeling tracks. It all depends on what happens with fracking, with rice paddies, permafrost dying, and other parameters and factors that need to be considered. So here is the same. We have the blue line is the monthly mean that we see here. Again, the up and down, the oscillatory nature is reflecting seasonal variation. Once again, we calculate a 12-month running mean through here. Once again, we see the 12-month running mean stopping before we get into 2020, because you have to wait for the previous 12 months. The overall trend is clear. Now, it's interesting what they did here on the graph. They broke it down into sections. So for the first section here, you can see the dashed red line from about 1984 or so to about 1993 or so. It increased by 11.5 parts per billion per year. Then from 93 or so to roughly 07, 08, it slowed down to 2.8 parts per billion per year. And then since then it's picked up again, 7.2 parts per billion per year. So why is that? Well, let's look at a section here from about 1985 through 2017. And what do we see here? If you look at the 60-month running mean, there is a decrease down to about 05. So now why is that? Okay, and this graph is showing the change in the CH4 per year. Okay, so why do we have this slowdown here, or the decrease in the amount of CH4 added per year? Okay, possible reason for the graph of methane on the right. The contributing factor for decline in methane levels could be all the cattle that were slaughtered, at least 4 to 6 million, due to mad cow disease. Now, this is my hypothesis, so I want to stress that. I could be completely wrong on this, but that is my hypothesis. I've been looking to see if there's studies that looked at that very question. As of yet, I have not yet to have found any. Doesn't mean none have been published. I just probably haven't come across it yet. But that is my hypothesis. So then a subsequent increase could be due to cow numbers increasing afterwards. So the mad cow disease and farmers, ranchers, cattlemen, whatever, start increasing the cattle, increase the reproduction rates and so on. So now you're adding more cows farting away. And what do cows fart? They fart methane. So you have adding the cow farts to the atmosphere, the methane. You have more rice paddies kicking in. Rice paddies produce a lot of methane. And of course, you got the fracking and then the outgassing from the permafrost. As seen why the uptick. But this is why I think we have that. I said, I could be completely wrong, but that's my thinking. Now we can look at nitrous oxide. Again, the same data sets. It's interesting to note that with the exception of the RCP model, where it shows a flattening, the other modeling extrapolation shows an increase, a continued increase. Again, it's in parts per billion. So this would be 0.44 parts per million and so forth. Nitrous oxide is a greenhouse gas, is now being shown to also be outgassed from the permafrost. So the permafrost, as it thaws, not only releases methane, it's releasing nitrous oxide. Couple that with CO2, couple that with water vapor, you have 4 very potent greenhouse gases whose levels are increasing in the atmosphere. You increase the air temperature, you can hold more water moisture, and thus these are all contributing to the increased warming that the planet is experiencing. But once again, monthly mean in green and 12-month running mean in the black. Again, the 12-month running mean ends before. I think they chose the green because if you ignite methane, it's a bit of a greenish flame that results. And over here is the change in N2O, parts per billion per year. Not sure why there's a gap here in the 60-month running mean, but it looks like there was some incomplete data for whatever reason. Okay. The trend is increasing. It's probably it's not a flat line, but it is increasing, but it's not as increasing as high as it does for the methane and the CO2, but it's still nevertheless increasing. So before we get into the next section, what's the take-home synopsis of what I just presented thus far for gases? Gas levels are increasing. Okay? And when increasing, we have significant slope. As you add more of the CO2 to methane and the N2O to the atmosphere, those are more greenhouse gases trapping more heat energy, thus helping to warm the planet. And obviously we know about burning fossil fuels, that adds CO2. Burning coal, well, you have permafrost. As it thaws, it adds CH4, N2O. Also, the fracking operations, rice paddies, more cattle, increasing cow flatulence that release methane. So, so in other words, these levels of gases are increasing the atmosphere, warming the planet. So that's the synopsis. This is the latest data that I'm bringing to you. So now let's consider temperatures, air and sea, long-term trends, July and August. Okay, this is going to be kind of a large section here. So I'll start with what's going on around Alaska. So looking at sea surface temperature departure from normal. So in other words, any area that is white, temperatures, there's no departure from normal. When you start getting into the orangey red, brickish red colors here, that's warmer than normal, so it's increasing, and blue is cooler. So oceans around Alaska are mostly warmer than average during August, and this is based on NOAA data, high resolution data. The major exception was in the offshore Beaufort Sea, where slowly melting ice kept the sea surface temperatures down. That's this region right here. That's the Beaufort Sea. Slowly melting ice, yes, you're going to cool down the surface temp water here. Alaska is still sitting in a cooler than usual situation here. Air temperatures are cooler than usual, and that extends out into the Yukon Territory, which is this region here. The rest of the Pan-Arctic is experiencing warmer than usual conditions. We know that Siberia has been extremely warmer than usual. And of course, we have the fires in Siberia. So I wanted to start with that. It's interesting around hugging the coastline, we see warmer temperatures. When you get into the Bering Strait itself, slightly warmer to about no departure from normal. Then when you get into the Chukchi Sea, that's further offshore, no departure from normal. And that reflects the general cool condition that Alaska has been experiencing for almost a year now. So now let's look at global surface temperature. So this is air and sea temperatures. And this is, looking at from 1880 to 1920, that's relative to this 40-year mean. So basically, they calculated a mean for this 40-year period, and these values are compared against it. So if it's 0, that means there's no departure from this 40-year mean. If it's negative, it's cooler than that 40-year mean, and this is warmer than that 40-year mean. And the black dots represent the January to December mean. So that's for each of these years here, right? And what do we see here? With the exception of dipping down into, and it's interesting, it's in this vicinity here, from 1900 about 1920, it was, or at least in here, it was a little cooler than average, and that's the only time period we see that. So the blue line is 12-month running mean. The red line is the 132-month running mean. That's 11 years. Okay, so 1 year, 11 year, and then they put in their best linear fit for the past 50 years, which is indicating approximately 0.2 degrees Celsius per decade increase. And you can see what happens starting at about 1975 or so. It just cranks. The arrows indicate super El Nino. These are very strong El Ninos, so they will tend to create warmer conditions. So they are accounting for that, but they are acknowledging that those events took place, which is why we see these really high spikes in the 12-month running mean. Overall, though, the trend is very clear. We're warming considerably. And as I say here, the last 12 months have been strikingly warm for our planet, and this is the source for this data, Columbia EDU. Now let's look at sea surface temperatures. This is the ocean, and that's for the January through August time period, starting in 1900 up to 2020. So again, this is departure from average. So here's 0, cooler, which is basically pretty much right before 1970. But again, from 1970 on, it's warmer. Again, the oscillatory nature is reflective of what month we are looking at. And this is water. This is an air. Remember, water has a high heat capacity. It takes more energy to heat it up. And if you were to fit a regression line here, you have a very definite positive slope. And you can probably take that positive slope right back to 1955 or so, showing a clear trend of how we're warming. This little spike here, I think, is 2012, which was a really very warm year. So the global mean surface temperature anomalies, okay, SST, departure from average, so far this year is the second highest on record. Data from NOAA sea surface temperature average over January to August. Now here is something I've been looking for a long time to find. And I consider this to be an extremely important graphic. What are we looking at here? 0 to 2,000 meter global ocean heat content. The red 3-month average, and they started early because they started around 2004 or so. That's because we've gotten sophisticated methods that can collect this data. Yearly average through 2019, that's the black line. And then pentadal average through 2015 to 2019. Pentadal means 5-year running average, or 60-month. So some of this extrapolation, there's going to be some uncertainty in the measurements going back into the 60s. But as the measuring, the equipment has improved, the technology has improved, our sampling has improved, and plus computer modeling, we've been able to get some very excellent data. So what are we looking at here? On the vertical scale, so going from 1960 to 2010, and so on, so 60 years. On a vertical scale, we have the heat content in 10 to the 22nd joules. So in other words, whatever value we read here, multiply by 10 to the 22nd, and that'll tell you how much joules. So if I look here, that's 5 times 10 to the 22nd joules. If I'm over here at 20, well, we express numbers using scientific notation as a number between 1 and 10 times the appropriate power of 10. So we wouldn't say 20 times 10 to the 22nd joule, but we would say 2 times 10 to the 23. So as I just explained earlier, you have a pentatile average, which is a 5-year running average, which is why it stops at 2019, because in order to compute it through 2020, we need the results from 2016 through 2020, and those results are not in yet. So, but we can still look at the yearly average through 2019. As you can see, this started in about 2006 or so. We're calculating a yearly average, and we are still able to calculate a 3-month average through April to June. So we can then calculate May, June, July, a June, July, August, September. We can, so that information will most likely update the graph here. But let's look at what this is telling us here. This is telling us that the oceans, remember, this is from 0 to 2,000 meters down, pretty much to the depth where you would find in most locations in the ocean. Somewhere between 1,000 and 2,000 meters is the permanent pycnocline. This is telling us that the oceans have been absorbing more and more heat energy down to 2,000 meters every year. It keeps increasing, absorbing more and more heat energy. What this tells us is very important. The oceans have been absorbing a great amount of the CO2 and the heat energy. But because there's also the density-driven thermohaline circulation, which are vertical currents, it is sequestering a lot of that heat energy down to depth. This is going to start changing. This will start changing as we're now seeing with the ocean stratifying. We're seeing the formation of vertical currents such as AMOC slowing down. In other words, the ocean's ability to keep absorbing CO2 is decreasing. So therefore, if the ocean's ability to absorb CO2 is decreasing, so is the sequestration of CO2 from atmosphere surface waters to depth is also reduced, which means it reduces the ability to sequester heat. Because as I said before, the conveyor belt is a heat distribution mechanism. You pull the heat out of the surface water, and you then distribute it and it upwells in other locations. But all that will be compromised. And this graph, this figure here is clearly showing that the oceans have been absorbing more and more heat, right? Just look at the energy level. I mean, let's just take 2020. Let's take the point here where the black line ends. And if you read that across, that's about 26. So that'd be 2.6 times 10 to the 23 joules. That's how much energy the oceans have absorbed, which, think about it, that's how much energy humans have put into the atmosphere, and much more. The ocean doesn't absorb all of the energy, but that gives you an indication of how much energy humans have put into the system and how much the oceans have been absorbing. So I would expect that as the oceans start to stratify more so, that we're going to see this plateau off, if not start to decrease a little bit. So this is, This is a very important graph, and it shows a lot of things going on. All right, moving on. So here we're looking at July 2020 temperature anomalies, as well as the ice cover at the end of July. But look at this here. Here's the Pan-Arctic view, and we have a cool spot in basic Central Eurasia. Scandinavia is a little cool. Alaska and the Yukon Territory are cool. But look what's going on here in Greenland, the Canadian archipelago, Western Eurasia, Eastern Eurasia into the Siberian region. Look what's going on here in the Northeast Pacific. It's setting up a very strong PDO into the positive phase of the Pacific Decadal Oscillation. But what we have here is the hottest July on record for the Northern Hemisphere. Second hottest for the globe, Arctic sea ice melted to record low. And that trend continued throughout, so that by September, we had one of the lowest Arctic ice levels ever. Second lowest overall. When you look at the Laptev Sea, there was no ice whatsoever. So I think I have some a figure that shows this side, this graph here a little larger. So we'll look at that in a moment. So here's the land ocean northern hemispheric mean through July. So in other words, they're looking at temperature anomaly with respect to, WRT means with respect to, the 1951 through 1980 average. So the black line is no smoothing. That's basically, so you're seeing the seasonal variation. Then we have lowest smoothing, which is, think of it as fitting a function through the points here. Last month was the hottest July on record in the Northern Hemisphere. So in other words, what this is looking at, this is starting from 1880 through 2020. These are the average temperatures for the Northern Hemisphere for the month of July only. And you can see starting about 1980, 81, 82 or so, it starts increasing rather dramatically. There it is. It's very clear what is happening. Okay, so here's that, going back. So right, there's that figure. This is it on a aspect. And this is, again, July temperature anomalies, basically showing similar information to the previous slide. And so now this is the 1880 to 2020 trends. It's 140 years. And the slope, this black line here is the slope, is showing overall a increase of 0.07 degrees centigrade Celsius per decade. That would be the slope of this line. It's positive, it's showing increase, but again, look at what's happening in starting about 1980 or so. It's all on the red. So this slope here is calculated over this 140 year. If you were to say recalculate it from say 1940 or even 1950, this slope would be higher. Think of, if any of you ever did anything in calculus, where let's say this is your curve, this is your function, right? Let me draw this curve line here. And you're asked to integrate from A to B, right? You would get a value. Then if you ask to find the total area, notice the area below the x-axis, the area above the x-axis, you would have to integrate from here to here, right? That would be one integral. You're going to get a negative result because it lies below the x-axis. So you take the absolute value of it, and you go from here to here, and then add the two results together. So if you ever remember from your calculus, when you integrate from A to B, and some of the graph is below the x-axis, what you're getting is an algebraic sum of pluses and minuses. If you want the total area, you need to find those sections of the graph that's below the x-axis, integrate that, take the absolute value of it, and add them all up together. Now, let's think of it as this were property, some piece of land, and you want to know your total acreage. Okay, how much is, let's say the x-axis is a road that runs through it. So you got this much on this side of the road, this much on the other side of the road. What I'm trying to say here is that because we're including this stretch from 1880 to about 1940, that's 60-year stretch there, that's actually tamped this down. If we were to look at it from 1940 or 1950 or even 1980, this value is going to be much, much higher. But the trend is clear for all to see. Yeah, this is for July. Here's this. I love this graph. Last month observed near or above average temperature in every band of latitude. Plot shows the zonal mean surface air temperature anomalies where latitude equals the x-axis. It's not scaled by distance. Okay, so here's the temperature anomaly. Okay, in other words, how much warmer or cooler it was for July. So in other words, this would be 1 degree C above. And again, we're going back to that 30-year average of, let's see, looking for the, yeah, this, that's the ocean heat content. There it is. This is what I'm looking for. Okay, so we're referring to the 51 to 1980 average. So this is the equator right here. So that would be 0 latitude. This line here, that's the Antarctic circle. As you can see, that's approximately 66 degrees south latitude. This is the Arctic circle. Antarctic circle, Arctic circle. Now you notice that this is probably a little more like 65 degrees north latitude, where this is 66 degrees south latitude. It's not symmetrical. That's the point here. But what do we see here? There's not a single latitude where it was cooler than that 51 to 80 average. Not a single one. This is basically over the Antarctic continent. And here we are. This is up here. This is 75 degrees. This is up here in the Arctic Ocean. This would be like northern Siberia, northern Alaska, into the Arctic Ocean. And you can see how much warmer it is. Now, what's going on here? Okay, that's close to 60 degrees south latitude. That's the only thing that's close to having very little, if any, deviation from the 30-year average. This is the approximate location of about 60 degrees south latitude for the circumpolar Antarctic current, or the Antarctic circumpolar current, which is, in other words, if you get on that latitude and keep traveling it, you're not going to hit a piece of land. It's all open ocean here. So you factor in the time of the year, the positioning of the to the sun, and so on, plus the specific heat of water. Not much. Didn't really warm up all that much there. But this just shows you, by bands of latitude, what's happening here. And as you can see, the data is from the NASA JISTEMP data set. So this is really cool. Shows a lot what's happening. A breakdown of latitude by latitude. So I particularly really like this graph. And here's again just showing you another view This blue here, where it's really cold, this is actually where we have the Antarctic deep current that formed. So by now you're familiar with the deep water formation up here in the North Atlantic. You also have a deep water formation off the continent of Antarctica, and that's what this is. That's what this is. Got really cold water here, so it cools off the air above it. So another month with just patches of blue. Overall, the average July global air temperature was basically 0.9 degrees C above the 51 to 80 climate baseline. And then if we want to go to the 1880 to 1920 baseline, 1.12 degrees C above that. So this is about near normal because you have the melt water coming off Greenland here. But basically, very, very, it's warmer than that the planet has seen. The black is where basically no data was available. So here's the 12-month running mean for global temperature. So now this is for the entire year, okay? And it's starting from 1980 up until basically the end of July into August of this year. So you can see it is following closely that graphic. Right, this one looks just at July. This is now looking at the year trends, 12-month running mean. So we're basically going from January to December, February through January, March through February, April through March, et cetera, et cetera. That's meant by a 12-month running mean. And as you can see, and this is for the last 40 years, starting in 2001, it's just getting warmer and warmer and warmer. Some of these dips might be a super El Nino, a little bit of a La Nina, and so on, which do help modify somewhat, but not by much when you consider that the scale is from 0 to just 0.75 above the average. So this is really just a dip here. Let's see, that would be about 0.68 or so to 0.5. So it's about a tenth of a degree. A tenth, maybe 1500ths of a degree at most. So it's not much of a, it looks like a dramatic dip, but it's not that much. And this is from the Copernicus European Union data set. Okay. So when I was looking at the ice and land and sea, and this one here, we're looking at the cumulative mass change, right? Loss of ice mass for glaciers around the Arctic. It does not include the Himalayas. So what do we have here? The purple is Alaska. That's this one here. Okay. Then we have this, I guess, olive green, whatever. That's Arctic Canada. Iceland would be this one here. Northern Scandinavia is this here. Then we have Svalbard, which is this blue one here. And then Pan-Arctic. This is basically a combination of all of them. So the black is the combination of what's happening all around the Arctic. And then they break it down by Alaska, Iceland, that sort of stuff here. And what we're seeing here is that the ice amount, how much ice we have, is drastically dropping off. It's melting. It's melting everywhere. Right? So it's decreased by, if we start with, say, 1950, and let's look at just Pan-Arctic overall, just to get the overall. So this is starting about 53, and so we have lost approximately, what's that, about 22, right? And we've lost about 22 million. I forget what the WE is for. It's not a union I'm used to. But we can see that there's a great amount of ice loss here for the whole Arctic region overall. July Arctic sea ice. Bang, down there. July 2020 was a historic month in the Arctic, from record low sea ice to anomalous warmth. There you have it. Look at what's right over the Arctic Ocean. Any small wonder why the ice melted away? And looking at the July for the Siberian sea ice, it really nosedives. It just, boom. Basically, you had the cumulative effect of all that specific heat, energy in the water, melting the ice, and whammo. And here we can just see, the temperature is just increasing. Increase to some of the highest levels ever. So it's just showing how the sea ice is rapidly disappearing. Now let's look at the Arctic temperature from May through August. Again, a warming trend. August 2020 was another month that the Arctic is yelling for you to pay attention. Direct quote from Zach. Right? So we see the temperature increasing. Not surprisingly, the Arctic sea ice decreases. Right? Temperature anomaly. Again, now it looks like eastern Siberia cooled down a little bit, but not after the damage was done, not after how hot we saw that was early in the year with all the fires and so on. The damage was done. Basically, what this is doing is reflecting shiftings in the Arctic dipole, which is the high and low pressure systems off Greenland and Siberia and so on. But we can still see it's hot into central Eurasia and the Arctic Ocean itself. And the Laptev sea ice. The latest data now tells us that in September, zero ice, totally gone in September. We see it right here. It's just about bottomed out. And by September, it has bottomed out. It is just now, there's hints of some ice forming, but this is the Laptev Sea only. But basically, the ice is zero sea ice, which is unprecedented. And we can look over the Chukchi daily sea ice. Okay, so the blue line, that's 2020. The green line was 2019. 2012, which was the year that had the lowest sea ice. That's this orangey line right here. And then 81 to 2010 median is this black line. In other words, 50% of the ice is above it and 50% is below it. It's the 50th percentile. This is the region from which the sampling is being reflected here. Chukchi sea ice extent now lowest in the satellite era for this point in autumn, with near record rapid sea ice loss. August 2012 was slightly greater. You can see that here and here. Big difference between multi-sensor analyses and passive microwave common in August. That's just the types of satellites that gather the data. But what's noteworthy to hear is look at 2019. You can see how the ice is rapidly melting off early. And then it didn't quite get to zero ice, but look, it didn't form up as readily. It did not form up as readily because the oceans were warmer, so it had to take a little longer for the oceans to cool down to start forming up the ice. In 2012, it dropped up dramatically, but then it started to quickly refreeze, and it even got to the point where it was above the median. And remember, September is the oceanic summertime. That's when we expect to find the least amount of ice because of the lag between involving the specific heat of water. As we continued through the rest of the summer for Chukchi, it further got to near minimum values, almost to zero ice. There we see continuing along. It's basically bottomed out. There's no ice. 99% open water. Beaufort Sea at 42% open water. Sea ice continues to melt. Winds next few days will push ice southwest into open water. That's this way. Where presumably lower latitudes will melt the ice. Here we are with the Laptev sea ice, right? And we will continue. If it continues through into September, October, it's at 0. No ice at all. Arctic sea ice annual minimum. So this here are the 1980s mean, the 1990s mean, 2000s, 2010, and then this is 2020. A couple little interesting locations of specific years. Again, as I said, September is the oceanic summer, so we expect the minimum to be occurring during the month of September. But we can see, and this is the extent times how many million square kilometers, we can see that the extent is dropping. Arctic sea ice extent minimum has already dropped to the second lowest on record in a JAXA data set. This is only the third time, 2012, 2019, 2020, being the years, that the total sea ice extent has gone below 4 million square kilometers. So that's here, here, and here. Definitely a trend. And this is showing these basically a 41 year average. Third lowest Arctic sea ice volume. This is volume. So this takes into account multi-year ice. Each line represents 1 year from 79, the dark blue, to the dark red, which is 2019. That's this one here. Data is from Biomass. Okay. Remember, September is the oceanic summer. That's going to see the minimum. Get into March, April is where you're going to see the maximum because that's oceanic winter. So we kind of a sinuous curve here. But again, you can see that the ice volume is decreasing as well as the ice extent. And you can see how 2020 is the second lowest. That's for overall Arctic sea ice, the whole basin. Now, I particularly like this graphic here. The rate of Arctic sea ice extent loss has increased. In particular, there's been a large reduction in sea ice concentration, fraction of ice in the Beaufort Sea. So before we get into this, let's explain what we're looking at here. The yellow, which you see right here, that's the median from 81 to 2010. It's a 30-year median. Okay. The light blue is the current year, 2020. Then we have this white line, which is the year 2012. We can see that that was the lowest extent recorded. So now, if we look at the, I guess call that kind of bluish one there, that's the 25th to 75th percentile. That's this region here. This is also referred to in statistics as the interquartile range because the 25th percentile is the first quartile, the 75th percentile is the third quartile, and so when you take 75 minus 25, that's 50. So in other words, this represents 50% of the data can be found in this spacing here. The purple is 10th to 90th percentile. Okay, so that's here to here, right? So this is basically 80% of the data. And then the gray is plus or minus 2 standard deviations. 2 standard deviation accounts for basically 95.4% or so of the data here. So in other words, what this is telling us is that from here to here, when we look at the Arctic sea ice for the 30 years that this data is looking at, we can find 95% of the data in here. So when we look at 2012, when we look at 2020, we see that it is what? It is outside this region here. In other words, this is highly significant. This is a highly significant loss of sea ice for 2012 and 2020. This would be considered significant. So I like this graphic here because you can see at a glance that this is a significant result. Whereas when we look at something like this, okay, these are the individual years. Then you do something like this and say, now you can see how it stacks up quickly. And it stacks up by being outside plus or minus 2 standard deviations. Remember your bell curve from statistics. So this tells us that the ice loss in 2012 and 2020 are highly significant. So continuing on again, we have, again, the same idea. They might have changed the colors around a bit. But so now the dark blue is the median. The current year is 2020. 2012 is the record minimum. That's this one here. Okay. This continues tracking well below average and outside 2 standard deviation at the end of August. Okay. So again, we still have the 10th and 90th percentile, and then we still have the plus or minus 2 standard deviation. And again, the light blue is the interquartile. Well outside. And if you look, let's, 2012. 2012 started out, look right in here, it's within, if you take that, for example, in April, it's within the IQR. It's still within the 10th and 90th percentile. It's still within plus or minus 2 standard deviations. And when you get into about late of mid-June or so, it then falls out of the plus or minus 2 standard deviations. Whereas 2020 started on the low end, excuse me, of the plus or minus 2 standard deviation. And for the most of this year, it's been outside the 2 standard deviations. So this is very telling at how rapid and how much the ice loss has been. And Arctic sea ice extents currently second lowest on record. 2012 is the lowest. So about 780,000 square kilometers less than the 2010s mean. About 1.9 million square kilometers less than the 2000 mean. About 3 million square kilometers less than the 1990s mean. And about 3.6, 3.7 square kilometers less than the 1980s mean. This is all courtesy of Zach Laib's data set. And you can see it's just lower and lower and lower. 80s, 90s, the 00s, 2010s. And there we are now. This means more open water, more energy being absorbed, not reflected into space. That's the bottom line. You have the less ice you have, the more energy is being absorbed by the ocean, the less energy being reflected back into space. Albedo's reduced, energy is being absorbed. This is going to help warm up the Arctic considerably fast. So here's the Arctic sea ice as of August 17th of this year. Now, this is the concentration. The whiter it is, the more multi-year ice it contains. The more towards blue and purple, that means it's less multi-year ice, more like first-year ice. It is also thinner, which means that some, unless it's covered by snow, some sun energy can penetrate through that ice, whereas the higher the concentration, more likely energy is going to be reflected back. Now, let's compare these two. This is now about 2 weeks later. This dashed line is the 85th latitude. So you can see, and this outer solid red circle is the Arctic Circle. The sea ice edge is up to the 85th north parallel on the Atlantic side. The poleward extent of open water is becoming increasingly common in the new Arctic around the annual minimum. But now, most of the ice is what you see off here in the Canadian archipelago. Okay, so here is the Chukchi Sea. Here is the Beaufort Sea. This is the East Siberian Sea. This is the Laptev Sea. Okay. This is the Kara Sea. And this is the Barents Sea. Here's Fram Strait. This is Novaya Zemlya. If you look on the Siberian side, or the Eurasian side of the Arctic, there is no ice. No ice. And couple that with how hot it's been in Eurasia and Siberia, it's very easy to see why that's the situation. Okay. And here's the ice edge right up to there. So and the reason why you have most of the ice on the Canadian archipelago end of thing is just because Alaska and the Yukon Territory were a bit cooler. Everywhere else in the Arctic was heating up. The last 12 months until recently, it was pretty much a little cooler in Alaska. Alaska this past winter had the coldest winter in 25 years, second coldest in 44 years. But this is very telling. There is no ice on the Eurasian side. Plain and simple. This is an excellent graphic. This is showing multi-year ice. So the purple, bluish, whatever, is 0 to 1 year old ice. The light blue, 1 to 2. This green, 2 to 3. This yellowish, 3 to 4, maybe golden harvest. And then you get into this orangey red, 4+ year old ice. This is a serious transition from older, thicker sea ice to younger, thinner ice. In other words, let's just take a look at, and going from 85 to present. Let's take a look at 4-year-old ice. It's basically gone. 3 to 4-year-old ice, okay? And this 4+, this is going to be 4, 5, or 6-year-old ice. So what is meant by, say, a 4-year-old ice? That's ice that survived 4 summers, didn't all melt. And so then it accretes and it accumulates. You get some of the, pretty much very thick and, several meters thick, 5, 10 meters thick, that kind of stuff. This is all disappearing, folks. All disappearing. And the multi-year ice, what's going to be left behind? A lot more of the younger ice. And that's what this graphic is clearly showing. Right? Clearly showing that. Again, here's your Arctic Ocean. That's the region that's being examined. So we see how the sea ice is becoming thinner and thinner. We're losing the multi-year ice. And so if you have younger ice, that can melt more readily, leading to more open ocean water. So we're on track to having Blue Ocean Event, the BOE, where I'm now seeing models saying 2022, 2024, we will have completely ice-free, and by that means no ice anywhere in the Arctic Ocean for at least a couple of months each year, and then building up so that by the middle of the 2030s, the Arctic Ocean may be ice-free year-round. Finally, a word about sea level rise. As land ice melts, sea levels will rise. Well, we've heard projections about what will happen, how much will sea level rise if Thwaites, Ross, Pine Island, Greenland, etc. Collapse, completely melt. How many meters will the ocean levels rise? Sea ice melting does not contribute to sea level rise. And don't forget about not only sea level rise, not only from glacial melt, from land input, but also from thermal expansion. First signs of such changes can be measured in tidal actions. The following graphic is an indication of this happening right now. Here we have sea level change from looking at basically the last 26 years or so. So basically, the brown is showing a decrease in sea level, blue showing increase, with dark blue the most. And this is in centimeters. So this would be 20 centimeters. Now, 30 centimeters is a foot. So 20 centimeters is about 8 inches. Sea level rise at many locations along the U.S. coastline. High tide flooding is now 300% to more than 900% more frequent than it was 50 years ago. This is from NOAAclimate.gov. Now, what's interesting is if you look in the oceanic basins, you see a lot of the dark blue over on the western side of the oceans. Here, and even off Argentina, and so on. Now, the question I had, and I have not been able to get a definitive response to this, and I've sent out my inquiries, is in calculating these things, has the westward intensification of oceanic gyres been accounted for? Because west intensification, basically, if you take, like, for example, the gyre in North Atlantic, I'm not going to get into the physics of it, but the thing is that you get west intensification so that the Gulf Stream is very fast, very powerful, and then by the time you get over here, the gyre becomes very broad and slow moving. Well, if you get in western intensification, you're going to also get a little bit of a sea level rise here. We're setting up what's called a geodesic heights. So I don't know if that was taken into account, but that if it were not, that could explain some of the signal. If it were, and then this is an actual true measure of the increase in sea levels, that's very telling. But you can see for most of the planet, irregardless of that issue that I raised, water levels are rising. Now, it's not just coastlines that get affected. If you have a major river drainage system, like you have the Mississippi, the Amazon, and other locations, if you start increasing sea level by a couple of meters, as some of the projections are for these glaciers, Thwaites, Pine Island, Greenland, start adding, it's not going to just be the coastlines that will see the rises, but you're going to see the river basins start filling up. Back in the Jurassic era, when sea levels were much higher than they were now, the continent of North America was almost split in two because there was an ocean, an inland ocean here, because sea levels were much higher. You start increasing the sea levels as such, we're going to see some similar things here. You're basically going to you're going to have the sea moving in here, creating a floodplain. You're going to be driving people out of their homes. So, get some acknowledgments. Many of the figures and diagrams presented in his presentation, the courtesy of Dr. Zach Laib, can be found at the following links. State of the Climate in 2019. So this is American Meteorological Society publication. So there's your big URL for that. NOAA Climate, climate.gov. You can just go to climate.gov. Other figures from Rick Toman for ACAP, Scott Duncan, others as indicated on the slides. A couple of interesting websites. JAXA, the Japan Aerospace Exploration Agency. And we saw I used some of their data set in this presentation. PIOMAS, the Polar Science Center, psc.apl.uw.edu. UW is University of Washington. So, here's some, for those who want to do a little further digging, here's some of the, where you can find some more information. So there's a lot going on here. I want to bring you, the data through that point here. There will be more updated data, of course, and they've already been released. But this is what this is through basically into August, into September, that I have readily available for myself at the moment. And so there you have it. So we can see how the Arctic is drastically changing. And the changes are major. It's going to bring on pronounced changes to the planet and will impact human civilization as well as the biosphere in general. Thank you for your time. I hope you found this informative. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.